Welcome everybody to Calculus BC. In today's episode, we're going to be discussing chapter 8.3, which is Logistic Growth. Logistic growth is very much stemmed off of the notion of exponential growth, which is what we studied in the last chapter. In exponential growth, let's go and do a recap of that first. Remember exponential growth, right? It always began with this differential equation. It was this differential equation of dy over dt equals ky. And what that basically meant was that the population would grow, like the rate of change of the population was always proportional to the amount present. We always looked for that word because of that k, the constant of proportionality. And we realized that this derivative here, this differential equation, produced a graph when integrated that looked like this. It looked like more or less that, a little less jagged, but I think we kind of get the idea. And so it produced a graph that looked like this. And well, what was this graph? This was our exponential growth function, right? After a series of separation of terms, integration, getting y by itself using some log rules, we learned that y, the function that modeled the population, was equal to ce to the kt, which was our basic exponential growth formula. Now, exponential growth can also be called something else. Some people call it growth without bound. And if you think about how that those words kind of, jive together, it makes sense, right? I mean, the longer the time keeps moving forward, the bigger the population is. The bigger the population is, the faster the population will grow. And so that seems to make a certain degree of sense with exponential growth. However, when you look at population growth as an actual model in the real world, exponential growth is not always the best thing to model said type of growth, because nothing really grows completely without bound. Everything happens to come upon a natural population curve or a population leveler. And so in order to understand how that works, in the 1800s, a French mathematician called Pierre-François Verhulst formulated a formula called logistic growth. And the differential equation for logistic growth looks like this: dy over dt equals ky. So just like exponential growth, if you look at the pieces, they look very much the same, except there's this 1 minus y over L that accompanies it, this piece that multiplies by the exponential growth portion. So what is this idea? What is up with this logistic growth equation here? I'll go and just type it in for you guys. A logistic growth differential equation here. So differential equation for logistic growth. Oops. Let's talk about what the pieces are doing here. So if we look at the pieces, if we look at the interactions, right? Y is being multiplied by k. That's that constant of proportionality. We know what that is. That's going to cause the exponential growth. That's the population being present, and the growth, being proportional to the population. What I really want to draw our attention to is this interaction right here, this y over L. What does L represent? And we're going to figure that out in just a second here. If we look at the relationship between them, if I was to say if y is much less than L, right? If y is less than L, think about what happens. And I would encourage you, if you want to, hit the pause button, see if you can think about what would happen to this differential equation if y was less than L. In other words, if y was to approach the value 0, what would happen, right? And so what you would get is you would get effectively dy over dt equals ky times 1 minus, if y was approaching 0, let's say y was 0, right, or super close to it, you would get basically essentially 0 here, and you would have something small here for y as well, but that's okay. What's really important is this part would eventually turn into 1, and this would go away, essentially giving you just dy over dt equals ky, which is where we started, right? So if the relationship between y and L was small, you'd end up with exponential growth, because this piece here inside the parentheses would effectively go to 1, and multiplying by 1 doesn't change anything. But let's take the other condition. If y is very close to L, so if y is very close to L. In other words, if y approaches L. Well, what does that do to the equation? What we have is we have dy over dt equals ky times 1 minus, now if y was approaching L, you would, in our differential equation here, essentially have L over L, right? So L over L, which would be 1, and these guys would go to 0, and the whole thing being multiplied would go to 0. So you'd have dy over dt equals 0. In other words, you would have no population growth. So what have I been trying to get with you? This L acts as what we call carrying capacity. Right, we call that carrying capacity. In other words, that's the max the population will go. And if you think about how populations work, it makes sense that there would be a carrying capacity, right? Humans cannot grow infinitely without bound. I mean, we would run out of resources. We'd run out of land. We'd run out of water. We'd run out of food. Natural things would start to happen that would start to curb our population. If you look at certain species of animals, the more they populate, the more predators they might have coming out of the woodwork, all kinds of stuff. So natural things start to take place that curb the population. And so what this graph ends up looking like here, and mind you, this graph that I'm going to draw is not represented by this differential equation. What this graph is what the differential equation will integrate into. So just like how dy dt equals ky integrates into an exponential function, this dy over dt equals ky times 1 minus y over L will integrate into the graph that I'm about to draw on the screen here. So I'll go and just do a little bit behind here, but it really starts at the y-axis, and it starts to grow a lot like exponential growth in the beginning. But what happens is that at some point it starts to S backwards and change concavity and start to head towards something, as you guys will very much appreciate, something like asymptotic behavior. In fact, it's not even something like asymptotic behavior. It is asymptotic behavior. These graphs have a horizontal asymptote at y equals L, because L is the carrying capacity of the population. So hopefully the graph of this thing makes sense. Hopefully the role of L now makes sense, because that is the newest thing introduced into our exponential model, turning it into a logistic model. So in a second, I'm going to talk about a few more things when it comes to logistic growth and this graph and the role of L, and then we'll do some examples. Give me a second. I'll be right back. Now that we have the graph of what the differential equation will integrate into, again, let's just remind ourselves what this differential equation is. It's dy over dt equals ky, parentheses 1 minus y over L. And so, to understand when the population actually grows fastest, right, because it looks like it grows pretty slow in the beginning. And as you approach carrying capacity, of course, the population will grow really slowly, or it may just kind of level off and not grow at all. We want to look for when the population grows the fastest. It's often a pretty important question. They ask this sometimes on the AP exam. If we look at this graph right here, and a reminder, this graph, if you put this function into like Desmos or something like that, you're not going to get this graph, right? This function is the differential equation which integrates into this graph. I got to make sure that's very clear. So if we look at the graph of the function, right? So I'll just go and call him y equals p of t, right? So it's a population. What would this thing? When would this thing be growing fastest? Well, remember back in Calc AB, we learned that if we were to look at the first derivative, right? The first derivative would tell us the way something was growing. So whether something was increasing, decreasing, local maxes, local mins. But if we wanted to find out how the increase was changing, we would take the second derivative, and that was measured by concavity, right? And when we saw that happen in Calc AB, where when something shifted from concave up to concave down, that was a local maximum of the first derivative, or if something shifted from concave down to concave up, that was a local minimum of the first derivative. So we learned back in Calc AB that points of inflection determine the rate of change. And so if I want to find out when does the population grow fastest, what I'm essentially asking is, what is the max of dy over dt. Right? Essentially, that is the question that I'm asking. So if I want to find out the max of dy dt, I better take the derivative of dy dt. Hopefully that makes sense. I'm going to go ahead and do that. So if I do d over dt of dy over dt equals, so I'll just go ahead and say, I'm going to actually go ahead and multiply this thing in. I'm going to distribute in. So I'm going to get ky minus ky squared over L. Now it's important to know that, remember, y is the only variable here, right? And so make sure that we are being mindful of implicit differentiation because it's definitely going to play a role. So what I'm going to get here is I'm going to get, I'll go and switch colors one more time. I'm going to get d squared y over dt squared is equal to the derivative of this ky here is going to be k, right, because that's a constant he's going to kick out, but d over dt of y is going to be dy over dt. And then minus, again, this 2 is going to come down like power rule, and I'm going to get 2ky over L. Again, implicit differentiation of the y, so dy over dt. So that looks like it's my second derivative right there. So I'm going to look for something that I can factor out. And again, why am I doing this? It's because I'm trying to find the max of dy over dt, right? And so whenever we were looking for the maxes and mins of a particular function, we'd always set that derivative equal to 0. So d squared y over dt squared, my second derivative will become 0 equals. Between these two, I think I can factor out a k dy over dt. So k dy over dt. What am I left with on the inside? I think that's going to be a 1 minus, looks like 2y over L. It's a minus, not equals. And so from here, remember, I'm trying to figure out a value of y that is going to make this statement true, right? What is the max of dy over dt? So ultimately, k and dy dt can be constants. I don't really need to worry about them. So 0 equaling 1 minus 2y over L. So at this point, it's pretty simple. I think it's 2y over L equals 1. So y equals L over 2, or 1/2 L. In other words, what this is saying is that when the population is half the carrying capacity, because remember, y is the function that dictates the population at any given time. When the population is 1/2 the carrying capacity, our growth, our logistic growth model is growing fastest. And that's going to be really important. And if you can identify that really quickly, it's going to be helpful. Now, actually, I made an assumption there because that could be a local minimum, but I will show you guys what that means. If I was to punch this thing into a sign chart, L over 2, and I was to look at this as a linear function, right? Linear function, it goes from plus to minus, right, at L over 2. So therefore, I can say, if I was to justify this on the AP exam, it would be d squared y over dt squared goes plus to minus at y equals L over 2, and therefore dy over dt has a max. And that is why this statement is true. Sorry, I kind of did that backwards there. So hopefully that makes sense. When the population is growing fastest, it's going to be when the population is 1/2 of its carrying capacity. I will be right back with some concrete examples of logistic growth, and I will see you in a second. So I've been talking a lot about the differential equation for logistic growth, but at some point it might be helpful to know what the logistic equation actually is. Like they might actually ask us, what is the population at that particular time? And if we don't have the function, it might be difficult or even impossible for us to figure out how many bears or how many gorillas there are at a particular time. So how do we figure out what the equation actually is? Well, we do have to go back to our good old buddy differential equations and separate terms and solve for the y after integration. So from here, what I'm going to do is I'm going to actually integrate this thing after separating terms. But there's a lot of algebraic maneuvers that need to happen, so just kind of stay with me on this. First thing I'm going to do is there are a few things I'm going to do to make this easier. like first I'm going to get a common denominator in here. The common denominator between 1 and L is L. So hopefully this isn't too fast. It's going to be L minus Y over L on that one. Now remember, to separate terms, I'm going to move all the Y's to the left and leave all the non-Y's on the right. So what I'm going to do is I'm going to, actually, I'll call him something different. I'll call him dy over dt equals k times y parentheses. And I'll make him very clear that that y is in the numerator. Because what I'm going to do is I'm going to multiply both sides by L over y times L minus y. And that's going to allow the entirety of this to cancel, giving me on the left now L over y times L minus y dy is equal to k dt. Now I'm going to get ready to integrate now that I've separated the terms. Now I want you to look really hard at the left side, and I want you to pause if you have to and think, why is it that we waited until now to teach you logistic growth? Why didn't we teach this to you in Calc AB? Because it makes sense that that you would learn it right after exponential growth, right? And so take a second and pause. I'll give you a second to think about why we waited until now to teach you logistic growth. Do you see it? This requires partial fractions. Our good old buddy partial fractions makes its triumphant return in logistic growth. So on the side here, I'm going to go ahead and say that L over y parentheses L minus y is equal to A over y plus B over L minus y. So I've got A parentheses L minus y plus BY equals L. So I'm about to do some risky business here. So I'm going to go ahead and say if I let y equal L, that means that the A part's going to go away. I'm going to end up with B equaling 1. Hopefully that makes sense. If I let y equal 0, the B is going to go away. I have A equaling 1 as well. Hopefully that makes sense. And then that means that what we have after the partial fraction mumbo jumbo is we've got the integral of 1 over y plus 1 over, looks like L minus y dy equals the integral of k dt. I would expect to be required to do this on the assessment this week. So just make sure you are knowing how to integrate partial fractions and logistic growth. So here's where a mistake's going to get made. When I integrate this, of course, I'm going to get ln of absolute value of y. Here's where the mistake's going to get made. I'm going to get ln of L minus y here, of course, but it's got to be subtracted because of the rule chain going on with the L minus y equals kt plus c. Combine logarithms, ln of absolute value of y over L minus y equals kt plus c. Now at this point, I'm going to do an algebraic maneuver, and it might seem a little odd at first, but I promise you I'm only doing it because it's going to make my life easier. You don't have to, but I think it'll make your life easier. So I'm going to flip the L minus y and the y. So I'm going to say ln of absolute value of L minus y over y, but I'm going to kick a negative on the outside of the ln because what happened is really the negative 1 exponent was here. I moved him down, so he ends up becoming a negative ln. The reason why I did that is because at some point that ln is about to go away, right? And when it comes to simplifying fractions, I'd rather have a binomial over a single nomial than a single nomial over a binomial. It just makes it easier to simplify. So now that I've done that, I'm going to go ahead and multiply both sides by negative 1 to get rid of this negative here. So I have ln of absolute value of L minus y over y equals negative kt plus c. Again, negative 1 plus c is still going to be plus c. That constant is a constant no matter what sign he is. We've been down this road before with exponential growth. I'm going to have the absolute value of L minus y over y equals e to the negative kt plus c. We've seen this happen before. This c is going to become e to the c. It's going to kick down. I've got L minus y over y in absolute value equals ce to the negative kt. So we basically have exponential growth, right? Except there's going to be a little bit more to it. The c, whether it's plus or minus, doesn't really matter. So I'll call him L minus y over y equals ce to the negative kt. At this point in time, it might not be a bad idea to solve for c. This might be a place where if it was necessary, if they gave you an initial condition. solve for C here if you want to. So in this case, now I'm going to go and say L over y minus 1. I just reduced my fraction here equals CE to the negative KT. So I have L over y equals CE to the negative KT plus 1. Multiply him over. I'm going to keep on scrolling down here. L equals y parentheses CE to the negative KT plus 1. And then I'm going to divide by the big thing here. So CE to the negative KT plus 1 gets divided out. And I finally have my logistic equation. Y equals L over CE to the negative KT plus 1. And there you have it. Now, again, let's take a look at the pieces. What happens as t approaches infinity, right? This thing here would be it would be multiplied by a negative k. The e would move to the bottom. The c, this whole expression would turn into 0, right? The ce to the negative kt would go to 0. I'll write that down. Ce to the negative kt would go to 0, and you'd be left with L. So only L remains. So it makes sense, hopefully, that there would be a horizontal asymptote at L, because only L will be remaining. The 1 would be on bottom. And so hence L being the carrying capacity. And so this is the function whose graph looks like this. Right? So if you were to put that, some variation of this into Desmos, you would get this S-looking graph here with the point of inflection and the horizontal asymptote and all that stuff. Hopefully that makes sense with the derivation of the logistic formula. Now let's do some actual word problems that contain the logistic growth formula. Give me a second. So in your prep books, there's a problem that deals with bear population here. And so it says the growth rate of a population of bears in a newly established wildlife preserve is modeled by the differential equation. I'll go and write this down. That way you guys can all see it. Look, it's dp over dt equals 0.8 p parentheses 1 minus p over 100. And it says where t is measured in years. Okay, so this is the differential equation that's going to integrate into our logistic function. Should be logistic growth. We see the exponential growth with the weirdness on the other side. And so a couple of really easy questions coming out of the gate here. So we're going to get you started with logistic growth pretty easy. It says, what's the carrying capacity of the reserve? Well, this is just an association problem, right? I mean, at this point, you have to just figure out where L is. So remember, in our original formula, it was dy over dt or dp over dt. There's a lot of different ways you can model this. Let's see. It looks like it's ky parentheses 1 minus y over L, right? And so what's playing the role of L right now? It's 100, right? So the carrying capacity is going to be 100 bears. That's it. That's all they can hold, just 100 bears. When's the bear population growing fastest? Well, we talked about that when we came to second derivative, right? 50 bears. When the population is 50 bears, that's when it's going to be growing fastest. And then what is the rate of change of population when it's growing fastest? This is the problem that requires the most math. And so what I've got is I need to figure out the rate of change of population. So that's going to be dp over dt at p equals 50. Well, that's going to be 0.8 times 50 parentheses 1 minus 50 over 100. So that's going to end up being, if you put this all into a calculator or if you do it all on your own, it's going to be about 20 bears per year. So logistic growth, while seemingly originally very involved, it's not terribly difficult because the questions that they ask are not, they don't seem particularly involved. If they ever ask you to do, to actually separate the terms, which we will see in the next problem, it gets a little involved, but that's all right. And there will be some calculator work in the next problem. So give me a second. I'll prepare my TI Inspire emulator, and I'll be back in a flash. In this next problem here, they talk about in 1985, the Michigan Department of Natural Resources airlifted 61 moose from the Algonquin Park in Ontario to Marquette County. It was originally hoped that the population P would reach a carrying capacity within 25 years with a growth rate of a differential equation representing this thing here. And so first off, I apologize for not capitalizing Michigan. That was a missing of the shift button, but that's all right. I think we'll be okay. Let's see. According to the model, what is the carrying capacity? This thing is filled with grammatical error, but that's all right. What is the carrying capacity? Well, remember, it's just about association here, right? The association is that 1,000 would be equal to L, which is the carrying capacity. So 1,000 mies. 1,000 mies can be carried by this differential equation or by this logistic growth model. That should be pretty relatively doable. Using a calculator in part B, this is the part that I want to focus on mostly. Do you think the prediction of the population reaching carrying capacity, in other words, 1,000 mies, is that reasonable within 25 years? So for that, I would like you to pause this video, get out your graphing calculator, a TI Inspire. That's going to be the calculator that I use. I already have it loaded up right here. And so, this is going to be our first time using the calculator for, in a long time here. So we're going to kind of mess with this. This is going to be partly a calculator tutorial. I'm going to hit this calculator button that's running away from somebody to get to the graph. In order to get to a differential equation, because remember, I don't know what this thing integrates into. I could solve C first, but let's say they didn't give me a part C with solving the differential equation. They just needed me to go from the differential equation. What would I do? Well, from here, I'm going to go here. I'm going to go to Menu, Graph Entry Edit, and I'm going to go to Differential Equation. So now I'm going to go ahead and type in the differential equation that we see in the problem here. I'm going to hit 0.3y times, and I'm going to open parentheses, and I'm going to say 1 minus, and I'm going to hit Control Divide here. And I'm going to put y over 1,000. And I'm going to hit my initial condition, which is 0 at time 0. I have 61 mies in the park. And I'm going to hit enter. I'm going to see what happens. And nothing happened. Okay, so from here, what's going on here? Why am I not getting anything? Well, a common error that can happen when it comes to working with the Inspire is it's the y. The y is the problem here. This y, it doesn't know which y I'm calling upon, so I have to actually identify that as y1. And if I hit enter now, I believe I get something, right? So I get a differential equation with this small little deal right here. So now, in order to fit my window, I'm going to go to Menu. I'm going to go to Window Zoom, Window Settings, and I'm just going to go from -1 to say 30, right? Because they said 25 years, but I'll go ahead and give myself a little bit of extra. The y min, I'm going to go ahead and give myself -1 again, -1, and my y max, I'm going to go ahead and call that 1,010. That way I can have just a little bit more of a window here. I'm going to hit OK, cross my fingers, and I believe within a few seconds we should have our initial condition showing up. And there we go. So notice the logistic curve that is tracked by this slope field. So what I'm going to do is I'm going to go ahead and trace. I'm going to trace this graph here, and I'm just going to keep on moving. Now, if you look at the 6.8 down here, that is the years, right? And then the 328.685, this is the population of mies in the park. So if I just keep on moving, look at what's happening here. I'm at year 18. I've got 934 mies. Doing pretty good. Whoa, have to kind of do that. Whoops, sorry about that. And if I go to 25 years, it's not bad. I've got 991.801 mies in the park. So let me go ahead and write that down. So I think that it's actually very reasonable that they would have, that within 25 years, they would probably reach their carrying capacity. 992 isn't far off from 1,000. So I think yes, it is yes. Their prediction is valid. There will be approximately 992 mies in the park after 25 years. So I think that's pretty good. Good job, Park. Okay, now it comes to part C, solve the differential equation with the initial condition of P of 0 equaling 61. I would highly encourage you to pause at this point and try and do this part on your own. It's always good to practice the differential equation, separation of terms with logistic growth. So go ahead and hit the pause button, and then if you want to, go ahead and unpause and then come back, and we will see how we did here. So I'm going to go ahead and start here. For those of you who have paused, thank you. I'll start with dp over dt equaling 0.3p times 1 minus p over 1,000. And we know that p of 0 equals 61. So what I've got here is dp over dt equaling 0.3p. I'm going to get common denominators here. It's going to be 1,000 minus p over 1,000. So now I'm going to go ahead and multiply both sides by, looks like 1,000 over p parentheses 1,000 minus p. So that's going to get me 1,000 over p parentheses 1,000 minus p. dp is equal to 0.3 dt. Again, this guy cancels this guy, these guys cancel, these guys cancel. So we're going to integrate both sides. On the side, let's go and do some partial fraction work. So 1,000 over p times 1,000, minus p is equal to a over p plus b over 1,000 minus p. So 1,000 minus p times a plus bp all over, not all over anything, equals 1,000. So if I let p equal 1,000, I get a equals 1. I get b equals 1. If I let p equals 0, I get a equals 1. So I'm going to have the integral of 1 over p plus 1 over 1,000 minus p dp equals the integral of 0.3 dt. So the integral shouldn't be too terrible at this point. ln of absolute value of p minus ln of 1,000 minus p. Again, the negative chains out for rule chain. 0.3t plus c. So I've got ln of absolute value of p over 1,000 minus p equals 0.3t plus c. Before I do any exponential conversion, I'm going to go ahead and flip this guy. I'm going to say negative ln of 1,000 minus p over p is equal to 0.3t plus c. Multiply both sides by negative 1. I get ln of absolute value of 1,000 minus p over p equals negative 0.3t plus c. Let's go and do some exponential conversion now. I'm going to move over to this side of the screen, and I'm going to get the absolute value of 1,000 minus p over p is equal to e to the negative 0.3t plus c. This c will come down and become the coefficient in front of e, so 1,000 minus p over p in absolute value equals ce to the negative 0.3t. Plus or minus c is just c, so 1,000 minus p over p equals ce to the negative 0.3t. Now, this would be a great place to pause and solve for c. So how do I do that? I'm going to do 1,000 minus 61 over 61 equals ce to the negative 0.3 times 0. That guy's going to go away. C equals 939 over 61. That's what c equals. So I'm going to punch that back into this version of the logistic equation. So I'm going to have 1,000 minus p over p equals 939 over 61 e to the negative 0.3t. Let's go and simplify this fraction on the left side here. So I have 1,000 over p minus 1 equals 939 over 61 e to the negative 0.3t. And now I'm just going to go get p by itself. So I'm going to go and keep on moving to the right side here. So I've got 1,000 over p equals 939 over 61 e to the negative 0.3t plus 1. Let's go ahead and cross multiply that p over. So 1,000 equals p parentheses 939 over 61 e to the negative 0.3t plus 1. And now I'm going to divide by the big thing. So what I have is 1,000 over 939 over 61e to the negative 0.3t plus 1. Just a reminder, the plus 1 is not part of the exponent. The plus 1 is existing on the outside. So what we have is we have a model for the population of meese in this national park. So quite a bit of work, but it's actually doable. It's very manageable. A couple of ways you can kind of make mistakes there, but make sure you guys are just staying on it and practicing. I have a couple more things to show you, and then that'll wrap it up for this video. I'll be right back. So the last thing I want to show you guys is what happens when the carrying capacity isn't clear. And so when it's not clear, what you do is, if you look in this first expression here, there's no L that's discernible. It looks like the carrying capacity is 1, right? But that wouldn't make any sense. It's pretty simple. When the carrying capacity isn't clear, factor. A little bit of integrate 2 in our lives. I'm going to factor out a 700. So if I factor out a 700, I'm going to get 0.56p, and now I've got 1 minus p over 700. You see how the carrying capacity is a lot more clear now. Carrying capacity is going to be 700. The growth rate is going to be fastest when the population is 350, whatever this population model is supposed to become. So again, factor out a 2 in this case. So that means that dp over dt, if I factor out a 2, that's going to be 0.24p, parentheses, 1 minus p over 1200. And again, with this population model, now we've got a 1200 carrying capacity, and that's a lot more clear. So that is logistic growth. There was a lot to it, but I don't believe it's terribly, terribly hard. As always, please leave comments or questions in the comments area. Congratulations on finishing up Chapter 8, all of the applications of integration. And moving on, we will get into some pretty interesting stuff into BC, stuff that kind of takes us back to Integrate 3 a little bit. It'll be quite fun. It'll be quite an adventure. So congratulations on being done. I will see you all in the next episode.
We should just watch the whole